Okay, let's go ahead and start the demo portion. The first thing we're going to take a look at is two-axis enhancements. So we've got a prismatic two-axis part. It's got a bunch of holes. One of the things that we're going to show you here is the enhancements in both the hole pocketing and in the thread milling. So in this part here, we have an M40 metric thread that goes through the base of this part. And in order to start that operation, or prior to starting that operation, we want to clear out, rough out the material, and get the inside diameter machined of that thread. So we need to do that ahead of time before we can do the thread milling. So let's go and look at hole pocketing here. So the first thing we're going to do is we're going to pocket out the hole and leave some allowance for the thread. So let's take a look at hole pocketing. Okay, so what we're going to do here is we're not going to select the whole perimeter, okay, because that doesn't represent the exact inner diameter of the thread itself. Okay, so we're going to select a point. Okay, we have selected a point right in the center. So we'll go on to the tool. So we're just going to use a flat mill, 12 millimeter diameter flat mill to hole pocket this out. For the cut parameters on the hole pocketing, the enhancement in version 2025 that we mentioned is compensation. So now you can apply cutter compensation right or left on hole pocketing. So we got compensation set to auto on, and we've got other cut parameters set. A few that's of note here is make sure you select the location of your cut geometry. In this case, we have selected a point, okay? And that point lies at the top of the hole. It's not at the top of the part, as you can see, but it's at the top of the hole, and that is at top, okay? So also, we have a hole depth that we just used the measuring tool to go ahead and calculate that depth. And we also have a hole diameter. Here's where I mentioned that we didn't want to use the diameter of the hole as modeled because we want to make sure that we're cutting to the minor diameter of the thread, okay, which will be smaller in diameter than this hole itself. So we calculated that needed to be 39.796 in diameter. So that's the minor diameter of the M30 metric thread that we're going to be thread milling in that hole. Okay, so one thing to note, you want to make sure that you're using a point so you can specify the diameter. If you check this and use arcs for diameter, it'll just cut to the diameter of the hole itself, and that's not what we want. Okay, so what else do we have on here? Everything is pretty straightforward. We're adding a cleanup pass at each Z level just to make sure we get the as much accuracy we can get out of the hole pocketing. Now the diameter of the hole pocket is not going to be the finished diameter. We're going to come back with a hole profile. So we can go ahead and go ahead and check that. That could be unchecked, but we'll leave it checked. Entry and exit. For typical for hole pocketing, we have a helical entry. So we got one helical entry at each cut level. So it's going to helical down and it's going to do a cleanup pass at each level. Okay, so we have a helix diameter of 1/4 of an inch or 6.35, and then we have a height H of 6.35. Okay, sorting, we're not going to do any sorting. We're only cutting one hole. And then also in 2025, we have feeder optimization parameters. We're not going to use those in this case. Okay, so let's just generate that. So we have a hole pocket. Okay, we got one helical motion, and then we have a cleanup pass at each cut level. If you look at front, okay, you'll see that we have a helical entry and then a cleanup pass. The blue motion is a cleanup pass at each cut level. So there's going to be 3 cut levels. Okay. Okay, so that is the hole pocket. So that's basically a roughing operation for this M40 metric thread, inside diameter thread. So based on that, let's go ahead and simulate that. Since we're at here, let's go ahead and turn the stock off. Now you will find that we haven't done any other roughing off, so you're going to see this hole stick up a little bit higher. Let's go ahead and play that. Okay, so we got the hole pocketing. Let's go ahead and look at the profiling. So in hole profiling, you have one helical motion to the depth, full depth of the hole, and then a cleanup pass at the base of the hole. So this cleanup pass is what really zeroes in the accuracy of this hole. So this hole profiling, let's take a look at that. We're using the same point, the same tool. So in the cut parameters, we have compensation on again, and we have location of cut geometry similar to the pocket at top. Okay, and the hole depth is the same at 19 millimeters. And then also for the hole diameter, we're using 39.796. That is the minor diameter of the hole. And we're going to uncheck use arcs, and everything else looks okay. Entry exit, we got lines and arcs, so we got a 1 millimeter entry, linear entry, and then also linear engagement, a linear retract. Okay, and let's see, that all looks good. No sorting, no optimization. Let's go ahead and generate that. So here is our hole profile, if you look at it here. So this is the minor diameter of the thread. Okay, so keep that in mind. We're not cutting all the way to the hole. Okay, so let's go ahead and show you what that looks like. So if you look at this is the M40 hole here on each side, and this is the helical motion of the hole profiling operation. Then we have a cleanup pass, circular cleanup pass at the bottom. And again, we have cutter compensation enabled. So now what we've got this set up. Let's go up here to isometric view. Okay. Let's change this view. Okay, so now we have the hole prepared and it's ready for thread milling. So let's go into the thread milling operation. So again, we're not going to use the point for the thread milling operation. We're going to use the circular diameter, because we're going to specify the parameters for the thread in the dialog. So this circular diameter is just more of a locator. So we're going to pick the tool, and as you can see, we have a tap tool. Let's take a look at that, or a thread tool. Okay, so we have a thread mill tool, and what's critical here is the 1.5 millimeter pitch. So this is the distance between thread to thread for the M40 metric internal thread diameter on this part. So these other dimensions that not that critical, obviously there's got to be, you know, smaller than 40 millimeters, but you're using a single point tap tool. So this tool will only have one thread on it. Okay, it's not going to be threaded all the way down. So we'll just have one thread. Okay, and the distance from the beginning to the end of that thread is the pitch of 1.5. So that's the major parameters that you need to make sure you got down correctly. The pitch diameter is critical, so that has to be correct. Let's exit out of that. So we have our single thread tap tool specified. So let's look at the cut parameters for thread milling. As I mentioned, the hole itself is just a locator because we're going to specify the diameters here. So we're doing an internal thread. It's going to be an M40 internal thread. We've got compensation on, cutter compensation turned on. It's available in thread milling as well. So we've got a right-hand thread and an internal thread. So the major minor, since we're doing an internal thread, it will be the minor diameter of the thread itself, and that's set to 39.796. Okay, and then a total thread length. This is set to 18 millimeters, but I think that needs to be 19. Set that to 19. The start depth, this means where in this depth you want to start cutting the thread. We want the thread to go all the way through from top to bottom, so the start depth is set to 0. And for the pitch control, we're setting it to a pitch at 1.5 millimeters. So that is critical. That has to match the tap tool that you're using. And 2025, we added some additional parameters. You can specify the pitch by threads per millimeter if you want to use that value. We also added a start depth if you wanted to give some relief to the thread. Okay, and a start angle, leave that set to 0 for the standard metric thread, and the number of starts is 1. That's for a standard metric thread also. So the entry and exit, you'll see that we have a linear entry of 1 millimeter, and then we have a radial engagement edge clearance of 0.6. Okay, we're not going to use any feed rate optimization. Let's go ahead and generate that. Okay, so here is our thread. So here is our M40 metric internal thread with a thread pitch of 1.5. So it's 1.5 between each thread. Okay. So when you, as you can see, you don't actually see the thread, and we don't actually simulate the actual shape of the thread, but the control geometry is there to create the thread. It's one helical motion, a thread diameter, okay, and it's got an entry, and it's got a helical ramp entry to the start of the thread, okay, and it's going and it's cutting at a pitch of 1.5 millimeters from top to bottom. So let's take a look at what this looks like when we post it out. Let's go ahead and look at the post for a moment. Okay, let's see what else we got. We got a couple of posts here. Haas CutCom, let's go ahead and select that. And we'll pick OK. And we're going to do the, when you run this on the machine, obviously, you know, this hole here at the big hole here at the top is all going to be cut out already. So we're just looking at the operations needed to do the hole pocketing and the thread milling. So let's do the hole pocket. Let's go ahead and post that. So what we got here is we got the hole pocket, and we have a G40, which is turning off the cutter comp. And then we got a G41, which turns on the cutter comp for that dimension. And that continues on down for the entire thread, or the entire pocket, excuse me. And it should turn it off at the bottom. Okay, so we got cutter comp in the hole pocketing. Let's go ahead and look at the hole profile. Post that. Okay, very similar. We've got a G40 to turn off cutter compensation at the start, and then we're doing a G41, turning on the cutter comp for the perimeter diameter of this hole. This blue motion here at the bottom, okay, that's the full cleanup pass. That's going to be assigned to the G41 where you can offset it at the controller. Now, just a note about cutter compensation. If you're not familiar with what it does, there are some misconceptions out there that it's only for compensate for your tool wear. Yes, you can compensate for your tool wear, but that's only going to come into play if you're doing production parts, okay? So if you're running 100 parts an hour, okay, you're obviously going to have a lot of tool wear, and every time you do your dimensional check, say every 100 parts or every 50 parts, you do your dimensional check, you can make those adjustments on the controller using the cutter compensation offsets for each of the tools. That's how it's used. One of the ways it's used in production. But in most cases, our users are not running production. Well, they do in some cases, but a lot of the users don't. Okay, so what would you use cutter compensation for if you're not running production? Well, think of it this way. Any operation that you cut, okay, you're going to have a setup, you're going to have stock, and you're going to have a tool, and you're going to run it. So the very first time you run it, okay, it may not be exactly positioned correctly, depending on the geometry, depending on the cut, what you're doing, okay. You may measure that while it's sitting right on the table, okay, and you may see that it might be a little off in the X or the Y, not because of the program, but just for the variations in how you might have set up the part on the machine, okay, where your work zero is, etc., etc. So what I'm getting at here is you can use the cutter compensation to dial in the accuracy, to make some adjustments at the controller to get this first piece the way you want it. Because your first piece in your particular application is the only piece, okay? So you can use that cutter comp to make some adjustments while the part is on the table, okay? So that's a good thing to remember about cutter comp. Okay, so let's also look at the thread. Let's post the thread out. Okay, so here's our thread. Again, we got G40, which is turning cutter compensation off. And then we have G... And then we have here a G42, turning cutter compensation on, okay? And it should turn it off near at the bottom. Right there, it's turning off cutter comp. Okay, so now, just as a recap, in 2020 version 2025, you can use cutter comp now in hole pocketing and hole profiling. Hole pocketing and hole profiling is the go-to operation if you need to cut a larger hole with exacting tolerances. For example, if you're going to press fit or do a slip fit or a loose fit of a bearing or a bearing sleeve, okay, you can use hole pocketing, specifically hole profiling, to get an exact hole diameter that you need without using a boring bar. And we have a video, and I'll put a link to it in the description, of one of our users using it exactly like that and getting the exact slip fit that he needed, no boring bar, just using hole pocketing and profiling. Okay, so we got that. Let's go on and look at the 3-axis. Our 3-axis part. This part right here. Okay, so let's talk about our 3-axis enhancements for version 2025. The one I'm going to show you here is we now have feed rate optimization available in all leveling toolpaths. By leveling, I mean not just 2-axis facing, pocketing, profiling, etc., but also in horizontal roughing, where you have flat level cut levels, and any other operation type that creates a flat planar area. Okay, so in this particular part, we have a couple of parts and they sit on top of a plane, okay, that we're going to use to machine them. So let's look at what we have here. We have horizontal roughing. Let's take a look at that. Okay, we got no control geometry selected, so it's just calculating what it can remove. We got a flat mill, quarter-inch flat mill, cutter parameters. These are all straightforward. You'll be familiar with all of these. Let's go ahead and look at the cut levels. So here, pretty much standard. We have an extra button here called Add Stock. I'm going to go over that in another part in just a moment. And then also engage and retract. We're using a helical engagement. We're doing some arc fitting. Toolpath optimization. So here, if you're familiar with our feed rate optimization in version 2024 and prior, you may know that feed rate optimization was an edit that we did after the fact. So you could only do it in a toolpath. Let's save this. I'll show you. You could only do it in the toolpath editor, okay? And if we go to the global edits, okay, and you'll see that we have a number of commands up here, and one of them is feed rate optimization. You'll see that all of the same parameters now are in this tab called toolpath optimization, the section called feed rate reduction parameters. So these are the same parameters. The difference is, the major difference, however, is that prior to 2025, feed rate optimization was an optimization that you applied to an existing toolpath that was already generated. Okay, so you go through your CAM phase, you have all of your operations generated the way you want them, and then you would go in after the fact, edit each toolpath to apply feed rate optimization, which obviously you probably figured out what the downside of that is, that if you make a change to the toolpath and regenerate it, the feed rate optimization parameters are lost. So you got to reapply them again. So the enhancement in 2025 is that we moved the feed rate optimization or the feed rate reduction parameters into the toolpath dialog so that they are applied when the toolpath is generated. So there's no other side steps that you have to do to get toolpath optimization implemented. So let's see what we've got for toolpath optimization for the horizontal roughing. The main thing to look at is the feed rate reduction percentage. So we want to reduce the feed rate 50% or 0.5 when it reaches a corner of less than or equal to 90 degrees. So anytime it comes to a corner that's less than or equal to 90 degrees, the feed rate's going to drop by 50%, okay? And then it's going to pick up at 100%, and these are the distances. Say an eighth of an inch before a corner, it's going to drop 50%. An eighth of an inch after the corner, it's going to go back to 100%, okay? So let's go ahead and regenerate this, okay? And let's go ahead and look at what the feed rates are. So we have a cut feed rate of 4 inches per minute. Now, in version 2024, that would be the cut feed rate throughout the whole path. It would not change. Come to a corner, your router will have to come to a complete stop and then start and stop, start and stop, and you actually can see that jerking motion on your router if you have a lot of sharp angles in your toolpath. Now we have other things you can do, such as some looping and stuff like that, which helps also. But now you can actually control the feed rates at those corners. So toolpath optimization, it's enabled, okay? And the feed rate is set to 4 inches per minute. Okay, so let's generate that. Okay, let's see what our post is set to. Our post is set to Haas CAM. I think that which should be all right. Let's go ahead and pick OK there, and let's post this and see what we got. Okay, so let's look at this. So our feed rate optimization was enabled. The feed rate was 4 inches per minute. Okay, so at the corners, we have a lot of corners. So at the corners, it should drop by 50%. So what you're seeing here is we got a feed rate of 4. It's dropping to 2, 50%. All the way through here, it's dropping 50% at corners. Anytime where you see an F2 is where it's dropped from an F4 to an F2. So this is feed rate optimization in action, and how it looks in your G code itself. If you don't see the reduced feed rate in your post to G code, you need to make sure that you have it enabled in the operation dialog, which is called toolpath optimization. Make sure that is enabled, and make sure you have the parameters set the way you want them to be set. Okay, let's cancel out of that. Let's see what else we have up here. So that was horizontal roughing. It also will not apply to horizontal finishing that's not planar. So we have a contoured parallel finishing. It will not apply to that situation. But if we go on down to the facing, this is a planar toolpath with a lot of sharp corners that will apply there. So let's take a look at the facing. So we have use optimizations is enabled, and we have the feed rate reduction percentage set to 25%. Let's take a look at what we have for feed rate. So we have the cut feed rate at 10. So in the corners, it should drop to 2.5. So this is 10 inches per minute. At the corners, it should drop to 2.5 inches per minute. Let's take a look at, it should be 1/8 prior and 1/8 of an inch after each corner. Okay, so let's generate that again. Let's post that. So here you'll see that we have a feed rate of 10. Okay, and at every corner it's dropping to 2.5. So all throughout the whole part, you'll see it drop to 2.5 at each corner. At the beginning, it'll drop, and then after it turns the corner, it will speed up to 100%. So that's feed rate optimization in action in 2-axis facing. Let's go ahead and minimize that. Let's take a look at the profiling. Okay, so your feed rate optimization is not going to, well, we do have it in there. You can apply it to profiling as well. Okay, so that is 3-axis feed rate optimization. Let's take a look at our next 3-axis part, which is, let's take a look at this one here, which is faceting controls. Now, you may have noticed, and this is only in certain surface cases, such as ruled surfaces. Let's turn our surfaces on. We got 2 examples here. Let's turn that off. Okay, so the problem the problem applies is when you have a ruled surface. A ruled surface is one that is a direct connection between one curve and another curve. So it's like a ruler. It's like you put a ruler on each of those curves, and you just run in the ruler down, you know, as it stays on both curves, and, you know, all the way to the end. So as you can see, that it's any cross section in this surface is a straight line, but it's a twisted ruled surface, which is a very complex surface. And in some cases, the actual internal generation of the coordinates and the facet points on that surface can get skewed. Okay, and this is a problem that we've been working on and fixed in version 2025, and a lot of users out there, if you're one of them, you'll be very glad to see this. So how do you implement this? If you go to the CAM Preferences dialog, go to the Machining tab, you'll see Meshing Parameters, okay? So what it's doing is it's using these parameters here internally to calculate the each control point on the surface that we're going to use to actually generate the tool path. So we have our part is in millimeters. So we have an aspect ratio, which is the relation between the length and the width of each facet in a mesh. If you're familiar with mesh geometry, you know that a mesh is a collection of planar triangles, okay, that define the entire object, okay? So we're setting the aspect ratio to 1.41. That's the relationship. Length divided by width is the ratio. And then we're also setting the maximum edge length. In this case, we're setting it to 1 millimeter. So let's go pick OK there. So if we look at the parallel finishing, before we set the meshing parameters, you'll see that there's a lot of jagged lines in that tool path as that tool rides over that ruled surface. This is bad. So you're not going to want to cut it like that. So what we've done is we've implemented the meshing parameters that once you set those and you just go back in and regenerate the operation, you'll see that it's cleaned up for you. Nothing else you need to do. You don't need to create a mesh in Rhino or in Visual CAD. You don't need to create a mesh to try to fix those errors in the toolpath. That's all fixed in version 2025. And we have another example. So here is a ruled surface. Okay, it's not as extreme in the other one, but it is relatively complex. We don't have a straight line here. We have a curve on this end with a straight line on this end, which causes the ruled surface to twist around. So let's take a look and see if we can see the problem. So here's our toolpath. And in order to see this, sometimes you need to have a really dense step over in order to see the phenomenon we're looking at. So you can start to see it. Let's go into the Simulate tab. Okay, so the part is turned off. So what you're seeing here, you're seeing those facets. Let's see, that's a good way to get it right there. You see those rectangular areas in the part or in the toolpath itself? Okay, so that will be seen when you machine this on the router. Okay, so now if you set the meshing parameters here, again, you set it over here, machining, meshing parameters, and we generate the toolpath. We added a second toolpath. You'll see that those faceting phenomenon are gone. So you will not see those in the machine surface. Okay, very, very sought after fix, enhancement, whatever you want to call it. This should not happen now in version 2025. Okay, let's keep going to some additional 3-axis enhancements. Let's go and look at, get my cursor back here. We'll go ahead and we're going to look at this one here. Okay. Now in 3-axis operations, you can combine, for your control geometry, you can combine both surfaces and curves, okay? And they act in a nesting type relationship. So in this particular example, we have a surface, okay? This is our base surface, okay? And then we have a feature on top of that surface that begins, it rolls up, off of that surface, okay? Now, to cut this, you may not want to cut this feature as part of the surface. You may want to just do the surface first, okay? So in cases like this, you can now select both the surfaces and the curves in order to get a nested effect. So let's look at the parallel finishing operation. So in this particular example, we have a part surface selected on the surfaces, part surfaces tab. Okay, so this is the green edges here. That's our surface, our base surface. And then for containment regions, we're selecting these perimeter curves. Okay, all the way around the base of this feature. So what happens now when you generate that, the inner curves will serve as a void region. So the tool will not violate these inner curves. So I know you may be wondering, well, you know, these curves are completely inside the surface. What happens if they don't? What happens if they fall off of the surface? Okay, so we'll get another example here. If you look at the top view, okay, look at the top view, and let's go into a wireframe for now. So we got the surface and we got a planar rectangle here, okay, that is partly on and partly off the surface. Let's take a look at how that looks like here. Let's turn the surfaces back on. Okay, let's go to, well, let's just take a look at it. As you can see, it just, you know, creates an void region where that, where the curve geometry intersects with the surface geometry. It treats that as an void region. Okay, so think of it as having a void regions in 3 axis, where prior versions of void regions basically you know, applied the 2 axis, but you could do it in 3 axis, okay, if you selected the curves in a certain way, like edge curves of the surface and edge curves in here. It will figure out that some of these curves are inside the other curves, but it's more of a complex situation. You could run into possibly some conditions where it could be a problem, okay? So now you can use both surfaces and curves together to generate your toolpath in 3-axis methods. And a lot of these 3-axis methods you will see that you can put both containment regions and part surfaces in the same operation. Okay. Okay, let's look up one part that I wanted to show you. I'm going to show you a couple of things on this part. Where is that? Right here. One of the things, an enhancement that we made to our professional configuration in relation to corner loops in 3-axis projection pocketing. Now, 3-axis projection pocketing, you'll see on the 3-axis advanced menu is projection pocketing. Okay, in projection pocketing, what happens is the toolpath is calculated on a plane. This is internally. It's calculated on a plane, and then those toolpaths internally are projected down in the z-axis onto the part. Okay, so the resulting toolpaths are 3-dimensional. They're not planar toolpaths. They're on the part surface. Okay, so that's just a quick definition of projection pocketing. So let's take a look at what we got here. Prior to 2025, in projection pocketing, let's take a look at that. We have a surface selected. We have our ball mill tool. Okay, and prior to that, you didn't have the cleanup loop. So this is what's new right here. You have corner cleanup loops, none inside and outside. So prior to 2025, there wasn't any, so I have it set to none. So what you get is these very sharp angles from one direction to another. Just as it can be a problem in planar, 2-axis planar toolpaths where the router has to stop and start at each corner. It has to do that also on 3-axis parts. So what we've done here, instead of implementing feed rate optimization, which I think there is in it, let's take a look. No. So there is no three-axis feeder optimization, but what we've added is the ability to add loops at these corners. Let's take a look at what that looks like. So on this one we have it set to, okay, corner cleanup loops outside. So this is the effect that you get. It's in effect, what it's creating is a high-speed toolpath in three-axis, okay, where the tool, instead of just stopping and starting, it can continue past, do this loop, go around. So each one of these angles here are less than 90 degrees, so it's a lot easier on your router, okay, and also on the cutting tools, and you get a better surface finish, because what you'll notice is if you don't have these loops, you'll have some material that may be cusping and left on the part in these particular areas where you'd have to go in either manually clean that up with a emery board or sandpaper if it's wood in this case, but with the loops it helps get rid of that excess material, have a better surface finish, less wear on your tool, very less wear on your CNC router. So that's three-axis projection pocketing in the professional configuration. If you want to look at these operations, you can run the product in demo mode in the professional configuration. We have a video for that on our website. Just go to MecSoft Corporation on YouTube and search for that, and you'll find that video. Okay, so what do we got next? Okay, there was one other thing I wanted to show you while we had this part displayed. So you've got your part set up. Okay, let's go back over here. Let's turn the world coordinate system. So we got a world coordinate system, and we have a work 0 up here, which appears to be at the corner of the stock. Okay, yes. So we got our work 0, we got our stock, everything looks good, okay? So you run this on the machine, and then you get an error on your controller, says machine limits exceeded in X or Y. In this case, it's X, okay? So then you're scratching your head, and you went, okay, so where do I figure out, how do I move my part to make sure it's inside that my machine limits, okay? And we actually get a lot of support emails on this. So what we've done in 2025 is we've given you the ability to see your machining envelope on the screen. So if you go up to the machine definition dialog and you set your min-max translational limits of your router, and these are values that you will find in your router manual. If you can't find it, just contact your router manufacturer and they'll supply those values for you. Just enter those values here, check this box, this is new, display translational limits, and you'll see that the limits display on the screen similar to a stock model. But let's look at what's going on here. We see that the part is too far outside the machine limits. So every toolpath on this part that exceeds past this translational limits in our plugin will flag as an error and alert you when you simulate that toolpath. If any part of a toolpath simulates and goes outside of this limit, then it will flag you and let you know before you get to the router and before your controller throws the error and you've got a part half machined and you're wondering what's going on. Okay, so this is a good thing to look at every single part. Make sure your translational limits of the machine is set in the machine tool setup dialog, and check this box and you can visually see your translational limits as it relates to your part and your setup. A very, very useful enhancement, okay, for 2025. Okay, let's move on. Our next enhancement in 3-axis is in adaptive roughing. Let's go ahead and look at that. Here we go. So we have a part here that we want to rough out these inner chambers using 3-axis adaptive roughing. Okay, now adaptive roughing is located here on the advanced 3-axis menu. If you do not see adaptive roughing on your menu, it means that you have not purchased adaptive roughing. Adaptive roughing is a as we mentioned here in the video, a module, sort of like a mini module. It's a technology that you can add to any existing configuration to use adaptive roughing. And adaptive roughing in and of itself is a method that during the computation and the calculation of the toolpath, it does a lot of adjustments based on your geometry and your tool and your toolpath parameters to get a very optimized high-speed toolpath. Now, what have we done? We've had adaptive roughing already in prior versions, but what we've done in this particular 2025 version, even we made a few tweaks and enhancements to it that I want to go ahead and show you. So let's look at the adaptive roughing dialog. We're using a 1/2-inch flat end mill. The cut parameters, everything looks pretty straightforward there. What we've done is in the engage and retract area where you assign the values for your helical entry. And in adaptive roughing, everything is about not slowing your tool down. We don't want to make your tool stop and change directions. We don't want it to stop at all. So in most cases at each cut level, you'll see one helical entry and one exit. You may see areas where the tool may have to rise and transfer, to get down to another area. You may see that, but even in those areas, we add arc motions to facilitate the high-speed cut pattern. So if you look at the entry, engage, retract, and material parameters, there's our helical motion, and also you can apply toolpath optimization if you want. But this is a method that cuts in levels. It's a roughing method. So let's take a look at the view the toolpath in levels display. So we got each one of these levels. Let's look at the first level here. As you can see, we have our helical entry, one helical entry at each level, but you'll also notice that we have a retract and a transfer to pick up some more material over here. So you'll notice here that in the retract, we have an arc motion and an arc motion and a retract motion, okay? So these arc motions facilitate the high-speed cut pattern itself at higher feed rates, okay? And then we also have arcs on the re-entry over here. So the enhancement is that we now enforce the helical entry at each cut level regardless of the depth of the cut level. In prior versions, the depth of the cut level may not have allowed us to put a full helical motion, or for whatever reasons, it may have skipped the helical entry and just plunged down to the entry point. You'll see now that we do not do that. We force a helical entry at every cut level, and we also add arc motions if you need to retract and move the tool to another location. So that's primarily the enhancement we did in 3-axis adaptive roughing. Okay. Okay, we got one more enhancement that I want to show you in 3-axis. Let's go over here. Let's turn the toolpath off. Okay, so you may have seen this part before. We've used it for a number of different things. But with the enhancement that we did in 2025, you'll notice that this part has flat areas. Okay, so we got a flat here, 4 flats up there, we got a flat in the center, we got a flat right here, We've got a flat floor inside. So if you're familiar with horizontal roughing, you know that you can clear flat areas automatically with the toolpath. So let's go ahead and look at the horizontal roughing. Okay, look at the cut levels tab. So what we've added is this checkbox to add stock. Okay, and by adding stock, what that means is users, a lot of you have asked for the ability, I don't want to clear the flat. Okay, I don't want to cut all the way down to the flat because I have a stock set to 25 thousandths. Okay, I want that stock to apply to the clear flat area. I don't want it to cut all the way down. I want to clear those flats myself with a separate operation. I have better control of it with a newer tool, say, to get an exact better either surface finish or an exact a better positioning of the flat, etc., etc., etc. Okay, so now what you can do is you can add the stock back to the flat area. So let's take a look at what this looks like. Let's go to the multi-view port. So we have clear flats enabled. We have clear flats enabled. We don't have stock enabled. So this is what it was like in 2024 and prior. And what you got was an additional toolpath at each flat area. Okay, so you have one there. You've got one down here. You've got one here. So it just interjects a flat area where it needs to. Okay, but the rest of these cuts are roughing operations. So you're leaving 25 thousandths on the part everywhere else, but we're forcing you to clear this flat area in a finishing operation. You may not want to do that, and a lot of users don't want to do that. So what we've done is we've added this checkbox, add stock to your flat area. I want to clear it, but I want to clear it at a stock value above the part. So let's take a look at what that looks like. So now what you'll see is we don't put that flat additional planar motion on the part. We move up by the stock value, in this case 25 thousandths. So you'll see that there's 25 thousandths left on your part that you can come in and you can clear off the way you want to clear it off. And again, here it is here, up 25 thousandths. And if we look at a wireframe, you'll see that inside, I believe that bottom floor is right here as well. We backed off 25 thousandths. So to reiterate, in 3-axis horizontal roughing, cut levels tab, clear flats, you also have this option now of adding stock. So if you don't want to clear your flats, but you want to cut the flats, but you want to leave the stock amount, just check that box, regenerate your toolpath, and you'll be all set to go. Okay, so that's it for the major 3-axis enhancements. Let's take a look at a 5-axis enhancement. We'll go down here, go here, go over here. Now this is it is a big deal in 5-axis machining. In a lot of cases in 5-axis, you're cutting complex geometry, and also you may be cutting edges off of a part. So you can think of if you have press punched a formed say a formed shell on a car body, just an example. Okay, you punch that car body, you have a blank, and you're punching the shape in the car body, but you need to trim out the edges of it. Okay, so you can use a 5-axis toolpath. Just put that that half-finished punched part on a fixture, and you can use this toolpath to go around and clean up those edges. In fact, they use this a lot with robotics to go ahead and cut and trim up things in 5-axis. In this particular example, it's a straightforward 5-axis continuous toolpath. In our 5-axis menu, it is the curve projection method. Now, in curve projection, this is a go-to operation type for cleaning up areas, okay, in around edges in 5-axis. And what it's doing is it's taking a curve that you select and it's projecting it. If you look at that operation, it's taking the curve that you select and it's projecting it downward onto the part, and it's cutting that curve in a 5-axis continuous motion. Okay, so in this particular part that you see here, what we want to do is we want to clean up this edge. Okay, it goes all the way around the part. Now, one thing that you'll notice if you look at this, let's take a look at this in this side view. Okay, in this side view, you see that this edge that we want to clear, it's pretty complex. So in 2020, prior to 2025, in 2024 and prior, on the 5-axis curve projection, you needed to create your curve at the location that you want to project it. Okay, well, in cases like this, you may not want to use this edge and project it directly onto it because it may ride up on, you know, this surface here. Okay, so you may want to move it over and then project it down to clean up this edge, and that's exactly what we've allowed you to do now in the 5-axis curve projection method. So if we look at this, so what you're seeing here is the toolpath without using the enhancement. So the enhancement, if you can refer to it as an offset and then a projection. So we're offsetting, in this case, without the offset, we're selecting that curve and it's attempting to project it down onto the surface. And if you look at the dialog here, in 5-axis, we have gouge checking. So we don't want that tool to gouge on this raised wall here. So we've assigned those surfaces as gouge check surfaces, which means the tool will not violate those surfaces for any reason. Okay, it's not going to violate it. But what that causes in version 2024 and prior is that the curve that we're trying to project down to clean up that edge is riding up on this surface because it doesn't want to violate it. Okay, so you'll see that it's raised up in this area. It might be closer in some of the other areas, like right in here. It's just not going to work. Okay, so you have to go in prior to 2025. You would have to go in, offset this edge, and create the curve that you want to project. That's a big deal because this is a very complex curve. You can't just offset this curve inward and project it down because this is a complex 3-dimensional 5-axis curve. Okay, so you can't just take one curve and project it down because it's not going to be the correct projection. So what have we done to help you do this? So let's go back up in this dialog, this 2025 options. So if you look at the cut parameters, we've added a cut side. So now we're still, if you look here, we're still selecting that edge, okay? But what we're telling it is we're telling it what side of this curve to cut on, and we can give it an offset distance, okay? So we're telling it to cut on the left side of the curve, okay? And we're cutting, in this case, we're cutting at a 0 offset. So let's take a look. Let's just cancel that a second. So what happens there is it offsets the tool and projects it down onto the surface in 5-axis mode. So that is an exact offset and projection of this curve that you've selected here. Now you can tighten this up or push it out, pull it in, however you want, but you see that it's not violating this edge whatsoever. Okay, so that is, if we look, can we look at the tool itself? Let's see here. Okay, so there's the tool if you look at it. Okay. So what we're doing, we're cleaning up this edge. Of course, we offset it a little bit too far. You can tweak that forward, or you can play with it and tweak it until you get that that edge cut the way you want to cut it without violating this wall. So that is somewhat of a complicated way of explaining a really complex problem that we've solved in version 2025. Okay, let's look at one more part. In this part, we're going to look at rigid tapping in hole making. So let's go, this is our last part, so we should wrap this up pretty quickly. So let's go down here. So what we have is a basic 2-axis part, and we've got this hole pattern. But what we want to do is we want to tap these holes using a rigid tap method. And in a rigid tap, rigid means that the tap tool and the collet on the tool is rigid. Okay, it's like one solid tool. And the also I want to mention that the rigid tap is a CAN cycle. In other words, it's one of the cycles that's built into your machine controller. If your controller supports CAN cycles, then you can use these to do drilling, tapping, boring, etc. Those are all CAN cycles that's built into your router that we can take advantage of when we post out to the G-code cell. So what do we have here? We have a rigid tap cycle tool path. Let's take a look at what it looks like. So we're selecting the 4 holes. Okay. We're using a rigid tap tool. Let's take a look at what that looks like. Okay. So this is our tap tool. The pitch is 0.041. Okay. And it can be a single thread tool or a multiple thread tool. Okay. I believe either way it should work fine. And this is the critical, as we did in thread milling and looked at the thread milling tool, the tap tool. Your thread pitch is the most critical dimension that you need to make sure you meet. Obviously, your tool diameter, etc., needs to be match the threads that you're tapping. But you know that should all be taken care of if you buy, what is this? A 3/16 or 1/88 tap tool or 3125 tap tool. All those dimensions will be in your spec sheet for the tool itself. So there's the rigid tap tool, and what the difference is here on the cut parameters tab, you'll now see that you have a rigid tap selection in the tapping types that you can pick from. So we have a tap, a PEC tap, a rigid tap, and then tap 1, 2, 3, 4, which are user defined cycles that you can define yourself. What we're talking about here is a rigid tap motion. So we're going to pick rigid tapping. The depth is 1/4 inch. The location of cut geometry is at top. Okay, the curves are at the top of the hole. The dwell, we have it set, we have it turned off. And for the tap direction, we're doing a right hand thread. We have an approach distance of 0.2, which means that the tapping tool is going to come down to 0.2 above the geometry, and then it's going to start tapping. And the feed rate is going to start going down on the z-axis to do your tap. Okay, so let's take a look at, let's cancel that out. Let's take a look at what happens in the post. So we got Haas rigid tap. Let's take a look at that. You'll see that down here in the cycles section, these are all of your CAN cycles. Okay, if your machine supports canned, as in a can, C-A-N-N-E-D, canned, so you have CAN cycles. If your controller supports CAN cycles, you'll be able to take advantage of all these different operation types in hole making. So here we added a rigid tap motion, and we have set up the cycle code here for a G84. All of this has been added in to create the G84 line of code, the CAN cycle code to post out to your router. If you don't see, this is not in there automatically in your post. If you want this added to your post, just contact us at support@mecsoft.com and we'll update the post for you. Okay. And let's see, that looks good. So let's go ahead and close that and post this out. Let's cancel that. Let's post. Okay, so we have 4 holes. We have a G84 CAN cycle that calls the CAN cycle on the controller. Okay, so you got 4 of them, and this is the line of code for your CAN cycle right here. Okay, so it's a G84. This is the X and Y location, the Z depth. Okay, this is the 0.2. This is the height at which the tap starts tapping, and then of course we have the feed rate of the tap itself. So this is one line of code that's posted out now that you can do for rigid tapping. Okay, that's it for the demo.